So today I will speak about some catalysts for ammonia synthesis in mild condition, and will show you the interest to use intermetallics sample. Okay, you always see my my new screen?
Yes.
It's okay. Okay, so ammonia synthesis is a very important reaction. It was a discovery by Fritz Haber in the early of the 1900 years. And so he was also awarded by the Nobel Prize for this reaction. So it is a very old reaction, and it is very important because it can fix the nitrogen from the atmospheric N2 compounds. For instance, if you can see in the graph here, we are report, it is a publication from Erisman. It was reported the total world population and the nitrogen use throughout the 20th century. And so in this graph, it is very clear that the solid line represents the total world population. And on it, we also plot in red dashed line the people that could be sustained without the reactive Haber-Bosch nitrogen. It was also reported in percentage in the black dashed line, the percentage of the world population fed by the Haber-Bosch nitrogen process. So to conclude from this figure, it is reported that by the end of the 20th century, around 40% of the world population depends on the fertilizers to produce food. In fact, ammonia can be used when you synthesize ammonia, you can use the nitrogen to produce fertilizers. So ammonia is one of the most important synthetic chemical compounds today and a key component of the modern chemical industry. So today ammonia production exceeds 180 million tons by years, and it is in continuous expanding, especially because ammonia was also identified now as a sustainable carbon-free energy carrier or a chemical hydrogen storage compound. It is reported in the figure where it shows that it's easier to compare to hydrogen to store ammonia, to store liquid ammonia compared to hydrogen. So ammonia show either on more widespread production, handling and distribution capacity, or better commercial viability, and also interestingly, an higher volumetric energy density. But the main drawback of this synthesis is that you need to use hydrogen to produce ammonia, and so historically hydrogen was produced based on the fossil fuels. So it leads to a very high amount of carbon dioxide emission in association with a very intensive dependency of energy of the synthesis, with around 2% of the total final energy consumption of the world. So the main drawback, the main challenges of this reaction is to reduce the dependence of the energy and the emission of carbon dioxide. And you can see here, this is a graph from the ammonia technology roadmap, that depending on the various scenarios you can imagine, you always have to deal with carbon dioxide emission. So you can use some carbon capture and storage unit or carbon capture on utilization. But the main goal is also to have better catalysts. Here in the graph, you have the equilibrium curve of ammonia production depending on temperature. And also the reaction is exothermic. You need to work at high temperature because the trivalent bond of F2 molecule is highly refractory. So to compensate the low yield achieved in this condition, you can also increase the pressure. So the industrial condition for ammonia process is at high temperature and at high pressure. So the goal is to develop new samples which can be able to produce ammonia at lower temperature and lower pressure. So the target are below 400 degrees C and below 10 bar. So to do that, the sample have evolved considerably since the beginning of the discovery of the process. At the beginning, the catalyst used was based on iron, which is abundant and inexpensive materials. But it is not simple catalyst. We have various kinds of iron species in this kind of catalyst. And at the beginning of the 19th, ruthenium was proposed as very highly efficient metals for ammonia synthesis, especially with so-called B5 sites, which are obtained with very low particle diameters, particle size, and which can help for the N2 dissociation by an elongation of the N2 bonds when it is adsorbed on this specific particle size. So in this case, the reaction is sensitive to the structure of the metals. We have also the possibility to increase the efficiency by doping this sample with electron donor elements, alkyl or alkane components. The best one is the cesium. And at the beginning of the 200th century, we have the new kind of catalyst based on the work of Norskov, which shows that we can combine two elements with very low or very high absorption energy for N2. And the combination of the two elements lead to a very efficient catalyst. So it was the discovery of the nitride sample, cobalt molybdenum nitride. And in this case, it was very interesting because with nitride sample, the mechanism for ammonia synthesis become a mass equivalent mechanism. And it's open new avenue for new process for ammonia production as chemical looping, for instance. And after that, we have a lot of publication with hydride or electrode sample. And in 2012, Kitano and Osono from the Japanese group proposed the first inorganic electrode, stable inorganic electrode for ammonia synthesis. It was a very promising sample because the electrode behavior helped for the N2 dissociation. And in addition, this catalyst can store a large amount of hydrogen as a hydride component, and it will prevent the ruthenium poisoning by hydrogen, by H2. So with this work, we will focus on this kind of catalyst. We use ruthenium supported on intermetallic sample. Intermetallics are so-called RTX sample was based on rare earth element, transient metal, and P-block elements. These catalysts were prepared by a collaboration with a lab in Bordeaux, in France, the IFCPAR lab. And this sample has the benefits to prevent both hydride and electrode behavior. So they are synthesized from the melting of the pure elements. They are finally arc melted and annealed at high temperature during very long time, during 4 weeks. And this has some metals samples, so they are very low specific surface area. So the hydride behavior comes from the fact that this solid can store a very high amount of hydrogen in 2 distinct sites, the tetrahedral and the octahedral one, leading to 1.5 hydrogen by formula unit of the solid. And this hydrogenation leads also to modification of the lattice parameter of the unit cell of the solids, which is very good news for us because we can obtain directly by XRD analysis the hydrogenation rate of the sample. They also have electrode behavior, and in this case, it only depends on the nature of the transient metals, namely that when the T element was the scandium one, samples present electrode behavior, whereas when it was titanium, they are non-electrode behavior. Okay, in this work, we will focus now on this RTX intermetallic compounds, and we will have a first kind of experiment on the impact of rare earth element in this sample. So in this case, the T and X element are fixed to scandium and silicium, and we change the rarest element from the lanthanide series, so from the lanthanum to the gadolinium one. Okay, so after that we will have another set of experiments, and in this case we do the opposite. We fix the rarest element to cerium, and we substitute the T element from scandium to titanium, or the p-Bourke element from silicium to germanium. Finally, of this sample were compared to a reference one, yes, based on ruthenium supported on basic oxide as MgO. So the ruthenium was deposited by a chemical vapor deposition technique, and the ruthenium working are between 1.3 and 1.9 weight%. Okay, so let's now speak about the results. Here we have typical experiments for the evaluation of ammonia synthesis performances of our sample. And we will monitor the reaction during time on stream, and depending on the temperature and the pressure. So in orange line, you have the temperature, which is comprised between 300 and 400 degrees C. And in green line, you have the impact of the pressure from 1 to 5 bar. In the left, you have the chem of the experiments. The ammonia was analyzed in line, in continuous, by a powerful infrared detector. This is a MKS instrument with a very low detection limit and very high speed of acquisition. So all of these results were obtained in the stoichiometric ratio between N2 and H2 for 100 milligram of catalyst. So first we'll compare the reference sample based on MgO to the most used intermetallic sample, which is based on lanthanum scandium silicium, which is the first intermetallic published in the literature. Okay, so what we can observe in first at low temperature and under 1 bar is that the MgO sample is not active. We don't have any ammonia formation at this temperature, but we can have a little amount of ammonia observed over the lanthanum scandium silicium catalyst. So it is around 100 ppm. It's not a lot, but it is an interesting result since the reference sample do not produce any ammonia in this condition. After that, when we increase the temperature, we'll have a formation of ammonia, of course, with a very important amount, and the intermetallic sample is presents higher performances compared to MgO catalyst, and will also have an important impact of the pressure. Okay, so this first preliminary results shows that we can have two temperature range for the next part of the study: the low temperature 300 degrees C and the medium temperature 400 degrees C. And we will now look at what's happening when we change the rarest element of the intermetallics, depending on these two temperatures. So first, at 400 degrees C, okay, we have some interesting results, and we have it appears that it seems that we have a good sample based on cerium. And also an interesting point is that some kind of intermetallics, this is the green, I don't know if you see my mouse, but this one present no activity. So the gadolinium-based intermetallic sample is equivalent to the reference MgO catalyst. It means that we don't have any ammonia emission of this intermetallic catalyst. Let's pass now at the result for the higher temperature. So here, it seems that we have ammonia emission seems to follow the lanthanide series. Okay, so the higher production is observed for the lanthanum and the lower for the gadolinium. Again, the gadolinium presents similar activities at MgO. But the important point in this slide is that it seems that the ammonia emission formation do not follow similar mechanisms depending on temperature. Okay, so the tendencies that we are obtained at 400 degrees C are not confined at lower temperature. So, if we look at now concerning the usual mechanism proposed in the literature, there are two mechanisms. The first one is a dissociative mechanism. In this case, we have the N bond cleavage is obtained before any addition of hydrogen. So the determining step is N2 dissociation. And the second one is the associative pathway. It is not exactly the same mechanism, since here the bond is broken upon the release of the first ammonia emission. So you can have a distal hydrogenation or an alternative hydrogenation, whatever, but you have the hydrogenation of N bond before the cleaving of the bond. So in this case, it means that the hydrogenation step is very important in the associative pathway. So we will try to have a better understanding of the mechanism. And first, we will study the N2 dissociation of this kind of catalyst. And to do that, we use a homomolecular nitrogen isotopic exchange experiments. So it means that you have to blend a similar amount of label N2, 14 and 15. And if you produce the corresponding N2, 40, 15, it means that you have the absorption and the dissociation of the N2 compound and the recombination to the wanted label N2 compounds. And in the other case, we also study the hydrogenation step of this catalyst. And to do that, we use the classic hydrogen temperature programmed desorption experiment. So let's go first to study the mechanism at 400 degrees C. So the results are presented here. Okay, so we inject N214 and N215, and we want to produce 4015 N2. So this is the results that we have in the graph here. So we can first begin by discuss about the graph in the right of the slide. It is about the reference MGO sample. It's very easy to explain this graph because nothing happened. So this sample, it means that this sample in this condition is not very active for the N2 dissociation, to the opposite of the intermetallic based on lanthanum. Okay, here you have a pure homomolecular exchange. You have a consumption of the signal blue and red, which correspond to 14 and 15 N2, and simultaneously you have the formation of the N2 4015. So the equation is balanced, and so you have a pure homomolecular exchange. So we can note that here, I don't show the curve for all the intermetallics in this study, but we have similar results, whatever the sample, whatever the intermetallics, we have a pure homomolecular exchange, but with different kinetic data. So the kinetic, the initial weight of equilibration, is obtained by the integration of the beginning of the slope in the as reported here, and we can obtain the initial weights for each catalyst. So it is what it is reported here. We have reported the ammonia weight production at 400 degrees C versus the initial weight of exchange. Okay. So remind that this initial weight is a good indicator of the ability of the catalyst to make the dissociation of N2. And so we have a good correlation, except for the gadolinium, which is a different sample. I will speak about this one after. But we have a good correlation. It seems to indicate that higher the N2, the activity of the sample to dissociate N2, higher the ammonia emission. So clearly, it is a good proof. We think that in this case we drive the ammonia synthesis by the dissociative mechanism. So intermetallic can help to the N2 dissociation by enhance the electron density at the surface of the air particles, and thereafter that we have a transfer of electron density to the antibonding orbital of the N2, which help to cleave the molecule. But what's happened if we want to perform similar correlation with ammonia emission at lower temperature? So in this case, we report the ammonia weight at 300 degrees C, depending on the initial weight for the N2 exchange. And in this case, we don't have correlations. Clearly, some sample present similar formation of ammonia, but with very various initial weights. So it confirms that we have another mechanism at low temperature. So if we come back to the previous slide, we go now focus the study on the stability and on the hydrogenation step of the catalyst. So, okay, we first begin by the three samples: cerium, lanthanum, and gadolinium, based on scandium silicium. And again, as previously presented, cerium shows the best results, and gadolinium present no activity for ammonia formation at 300 degrees C. And if we report in the slide also the curve of the hydrogen desorption depending on temperature, we observe here that the sample based on gadolinium don't have any hydrogen desorption. It means that this sample is not an hydride sample. Okay. It was confirmed by DFT calculation, so it explains the difference in the catalytic behavior of this solid. But to the opposite, clearly we have an important desorption of hydrogen at low temperature for the cerium, scandium, silicium. So it means that the stability of hydride is maybe involved in the ammonia synthesis pathway at 300 degrees C. Okay, now we will discuss about the result concerning the cerium-based catalyst. So we have the substitution of scandium by titanium, this is the blue to pink, and the substitution of silicium to germanium as the P block element. Okay, so in first, if we want to check the ability of this sample in the N2 dissociation, we can look at the result for the homomolecular exchange. So we already discussed about cerium, scandium, silicium, or lanthanum, scandium, silicium. We know that they are very active for N2 dissociation. It is the curve here. But when the P block element was changed, and where the sample was used germanium, in this case, we don't have any exchange activity. So again, it indicates that the good activity observed on cerium, titan, germanium, for instance, don't come from the ability of the catalyst for N2 dissociation. But again, if we come back to H2TPD curve, we always have a very important emission of hydrogen at low temperature. So it confirms really that the stability of hydride is involved in this mechanism. So based on this curve, we calculate two specific parameters. The first one is the amount of hydrogen desorbed up to 300 degrees C. We can make the integration of the curve and obtain the amount of hydrogen available in this sample at the temperature where the ammonia production was performed. We can also try to calculate it. It's not easy, but in this curve, but you can try to calculate the apparent energy desorption of H2 with the Arrhenius plot, and you can have some data at the beginning of the slope of the curve. So what's happened if you try to make a correlation between the ammonia weight and this various parameter in terms of H2 desorption, this is the square meter, or the apparent energy desorption of H2, this is the circle. So we can say what we want about with this kind of graph, but in fact, higher the amount of hydrogen desorption, higher the amount of ammonia weight, and also higher the H2 desorption energy, higher the ammonia yield. So it's quite surprised, this kind of results. You can explain this maybe by a competition between the NH6 desorption and hydrogen desorption. So it means that if you have higher H2 desorption energy, maybe that you can help the NH6 desorption and increase the ammonia yield, but it's not so easy to explain. We also perform some transient experiments. So in this case, it is like a chemical loop. In this case, the catalyst is submitted under pure N2 or pure H2, and you can switch between these two gases. So, in the top of the slide for lanthanum scandium silicium sample, ammonia is emitted only during H2 pulses. This means that certainly you have a N stored at the surface of the catalyst. I don't know if it is NH compounds or just N compounds or N2, I don't know. But ammonia is emitted under hydrogen pulses. So you cannot form ammonia under pure N2 in this sample. But it is not the case with cerium-based catalyst, because you can see here that ammonia is also produced, whatever the formulation of the sample, ammonia is also produced under pure N2 pulses. It means in this case that the hydride phases is involved in the mechanism. Okay, so to conclude, we have studied the ammonia synthesis on this kind of intermetallic, okay, at atmospheric pressure. They are more active than the reference sample. At high temperature, at 400 degrees C, we have no doubt that electrolyte character help for the N2 dissociation, and we have a dissociative pathway for ammonia production. At lower temperature, the hydride behavior and the ability of the sample to provide hydrogen help for increases the ammonia yield, and it can be explained by an associative pathway, for instance. Okay. So I thank you very, very much for your attention, and it was a pleasure to be with you. Thank you.
Long live India and France friendship.